So yesterday we were trying to complete a question, question 4. So what I'm going to do, I'm just going to complete B and C here. So I believe you guys have access to Prelego. I'm going to be very fast. So yesterday we were able to calculate the first part of the question that says um, you must determine the reaction in the two support. If the reactions are equal, we are to calculate the position between the support at which a concentrated load must be applied if the reaction between the two supports is what? The reactions are equal. So we were able to get that. So today we will just continue with the B part and the C part. So very quickly, so I'm going to be reading from my textbook, and I believe you also have your text. So for the B part, it says that we must determine, the question says that we must determine the reaction in the two supports. They said if the reaction in the two supports are to be equal, but a concentrated load of what? Of 1000. So I would say that for each and every question, you have to draw a diagram. Okay, so still, we're going to use, they said the reaction is the same. So we're going to calculate the reaction out now. So I'm going to use RL with RL. Upward forces equals to the downward forces. So the downward forces are the weight, which is 588.6, plus in this case now, we are to test with a load of 1000. So let's just quickly determine that. So this is going to give us 1588.6. So the reaction on the right and the left is the same. So we are going to get 794. You can also type, you can also punch the answer and just confirm 394.3 what? Newtons. Okay, so for this particular one is 794.3 newtons on the left and 794.3 newtons on the what? On the right. So we are to calculate the position now. So with the position, remember we have a load of 1000 newtons. So let's take our moment. The same process. So with the distances, they said this is 1 meters from this point, and then this distance is 2 meters, and this distance here is 3 meters, just to complete the diagram. So summation of moment, let's say this is the left hand side, and let's just say this is A. So summation of moment about the right hand side is equal to 0, right? Let's just remove this, it's fine. Don't have to label the section. So this is R. So let's take moment. So with the moment, this one is going to be clockwise. This one is going to be anti-clockwise, and the 1000 is also going to be what? Anti-clockwise. So quickly, we're going to have the clockwise moment, which is 794.3 multiplied by the distance between the two supports is 5, is going to be equals to 588.6 multiplied by the distance between that the load at the center and the support on the right hand side is what? Is 2. Then plus 1000 multiplied by x, which is 1000x. Can someone give me the value of x there, which is the position? Okay, you know what? Let's take moment about the left hand side, because now we are getting different. And let's take moment about this point so that we know that the position is going to be x distance from that point. So let's take moment about the left hand side very quickly. So it's going to be 794.3 multiplied by 5, right? It's going to be equals to 588. This is 588.6 multiplied by 3, then plus what? Plus 1000x. 2.2, yeah, 2.205. So x is 2, thank you, 2.205 from the left. 2.205 from the left, because we took moment about the left hand side from the left, hand side, just the way we did these ones yesterday. Let's look at the last part of the question. They said with the last part of the question there, let me just quickly label this. This is 1 meters, this is 2 meters, and this is 3 meters. The condition there for the last one, which is 4C, they said if the reaction in the right hand support, the reaction in the right hand support is twice, is linear online there. So the reaction on the right hand support is twice that of the left, and then the concentrated load there is given to be what? 400 newtons. So we do the same upward and downward force, summation of upward forces equals to summation of downward forces. So with the upward forces is right hand reaction plus the left hand reaction equals to the downward force is going to be the weight of the beam, 588.6 plus what? Plus 400. So we will replace the right hand side is what? With 2RL plus what? RL equals to 588.6 plus what? Plus 400. So this is going to be 3RL equals to, this is 988.6. Okay, the reaction in the left hand side, 988.6 divided by 3. Guys, I realized that we spend too much time on one question. So this is 329.5 what? Remember, the reactions are not the same. So the one that we got here is the one on the left, which is what? 329 point what? 0.53 newtons. Now we can now determine that on the right hand side. So the one on the right hand side, we can calculate that here. So we multiply 2 times what? 329 point what? 0.53. So the reaction on the right hand side times 2, double of that is going to give us what? 659. Let's say 659.0659 Newton. So this one is what? 659 newtons. So let's calculate the position. Let's calculate the position. Let's take moment about the left hand side. So let me start from here. Just see because of space. Summation of moment about the left hand side equals to 0. So about the left hand side, I'm going to have 659 multiplied by 5. That is anti-clockwise. So my clockwise moment are, this is 588.6 multiplied by 3. Then plus 400 what? X. Can someone give me the value of X here very quickly? 3.823. Thank you. From the left. From the left hand what? from the left hand side. So we are done with that question now. Just going to give you maybe 1 or 2 minutes just to write this down. Then we move to shear force diagram and bending moment diagram. I'm giving you 2 minutes just to write this down. Then we move to shear force diagram and bending moment diagram. Okay, just like I said that you're welcome. Just like I said that most of us are already familiar with the concept of um, beams and also the concept of shear force and bending moment as well. I'm just gonna do a quick recap of this, then we move to the question. So for those of us that this is new, so when we talk of shear force diagram, let's define shear force itself. A shearing force at any section of a beam is the sum of all the forces to the left or to the right side of the section of the beam. So you can see there are some diagram here. So this indicates positive shear and this indicate negative shear. So you can see there is something called um, sign convention. I'm going to be showing you how to. Okay, there is something called sign convention. I want you to take it. I want you to take note of this. We are going to be using this sign convention when we are calculating the bending moment at each section. So with sign convention, just going to be indicating that this is when the arrow is pointing down. I'm going to be making use of these things a lot. And then when the arrow is this is when the arrow is pointing up. Okay, so with the concept of sign convention, when the arrow is pointing down, this indicates negative. Use negative sign, and when the arrow is pointing up, we use positive sign. Now you're going to see this when we are calculating bending moment at each section of a beam. So what is a bending moment? A bending moment at any section of a beam is the algebraic sum of all the moments about the section of all the forces to the left or to the right. So we'll see how this is being determined. So when we have a beam that has a support, and then each and every beam has a section. So let's say this is L and this is R. We have section A and section B. And then the distance between this support is also given as well. It is very important that we know how to determine the bending moment at each and every section, the section where the force is acting. Like now, assuming we have a force acting on section A and then we have another force acting here, it is very important that we know how to determine the bending moment at section A and at section B as a result of the concentrated load that is acting at that particular section. It's very important. Okay, so let's see how this is done. We're just going to use this to just explain the concept. Okay, so there is a question here. This is 22 marks, 8 marks, 6 marks, 6 marks. Let's look at this question here. This question says that a light uniform beam A, B, C, D, E. So the A, B, C, D, E, these are the section of the beam. You can see A, B, C, D, E. So those are the sections of the beam. So majorly these are parts where the forces are acting. Okay, as indicated in the figure below. The first question says that we must determine the reaction forces at a reaction at A and reaction at D. I believe we can calculate that. That's the first thing that we are expected to calculate. RA and what? And RD. The distance between the support is 8 meters, isn't it? Distance between the support is 8 meters. Let's take moment, summation of moment about D is equals to 0. Now, I want us to take note here that we have two uniformly distributed load here. So we are going to have a concentrated load of 40 Newton there. You multiply, they said the load is 10 kilonewton per meter. So in order for you to determine the concentrated force here, is going to be 40, 10 multiplied by 4 is going to give you what? 40 newtons. There is another one here that we also need to derive as well. We have a UDL of 8 kilonewton per meter over 2 meters. This is 16 what? 16 kilonewtons. Kilonewtons. So this is 16 kilonewtons. Let's finish what we started. Let's quickly determine the reaction. So I'm going to take moment about D. So it's going to be RA multiplied by 8 is going to be equals to, let's determine our, so this one, we are taking moment about this support here. This is going to be clockwise. The 40 is going to be counterclockwise. 20 is going to be counterclockwise. This is going to be counterclockwise. 16 is going to be clockwise because we are taking moment about this section. Okay, so I'm just going to add 16 there. It's going to be plus. I want to deal with the clockwise moment for this. Is going to be 16 multiplied by half of that. It's going to be 16 multiplied by 1. Because the half of 2 there is what? Is 1. So that is middle there. Okay, so now let's deal with the counterclockwise moment. The counterclockwise moment, which is 40 multiplied by the distance there is 2. The distance between this point and this point is 2 meters. 2 plus 2 is 4. 4 plus 2 is going to be what? 6. So it's going to be 40 times 6. Then plus, I have 20 multiplied by what? 20 multiplied by 4. And then plus 30 multiplied by. Can someone give me the value of the reaction? So this is going to be 8RA plus equals to, this is 240 plus 80 plus what? Plus 60. Can someone just give me the value of the reaction there? 45.5. Thank you. RA is 45.5 what? Kilonewton. So let's calculate the second reaction. So we can use summation of upward forces equals to summation of downward forces. So the upward forces is RA plus what? RD equals to the downward forces, which is the point load T, is going to be 40 plus 20 plus what? Plus 30 plus what? Plus 16. So we substitute RA to be 45.5 plus RD equals to 40 plus 20 plus 30 plus what? 16. Can someone just give me the value of RD from the calculator? 60. Thank you. The reaction there is 60 point what? 0.5 kilonewtons. Now, remember the question says, oh, that's the first part. Calculate the bending moment at A, B, C, D, and E, okay? Now, the B part says that we must calculate bending moment. We are going to calculate moment at A, to what? E. Now, the bending moment at A is equals to 0. The bending moment at the tip, the bending moment at the far right end is equals to what? 0. So this is 0 kilonewton meters. The same thing as bending moment at E is also what? 0 kilonewton meters. Because they are at the what? They are at the tip there. Okay, so we just need to calculate the bending moment at B and the bending moment at C. This is where we are going to be using the sign convention. And I want you guys to concentrate the sign convention. When the arrow is pointing up, positive. When it is pointing down is what? Negative. Okay, let's see how does this sign convention works. Now, we want to first calculate moment about B. Okay, there are two that you can use to do this. You can work from the left to the section, or you can work from the right to the section. If you work from the left to the section, or you work from the right to the section, you are still going to get the same answer. So you just have to look for the one that is convenient for you. Look for the one that is convenient for you. Okay, so do here is you and I'm going to work from the left because from the left it has less forces. So now I have calculated my RA 45.5. Let me indicate that here. This is 45.5 what? Kilonewtons. And my RB is what? 60. This is 60 point what? 5 kilonewtons. So this is where you draw the beam and then you have to indicate the support there. Okay, now all the forces are there now. So I'm going to be working from the left hand side. So the bending moment about B. Now, so this is how it works. Now, if you look at the reaction at A here, it's pointing up. It's pointing up, right? So that is positive. So you write it as 45.5 multiplied by, we are taking moment about B. So the distance there is what? Is 4. You write plus. There is another force that is there, right? There is another point load that is there, which is what? 40 kilonewtons. So that force is pointing down, isn't it? So it's going to be minus 40 multiplied by the distance from that point to B, which is what? 2. Someone should give me this answer. The moment about C. Now let's check a bending moment about section C. I'm going to work from the right now to the left. And I said, whether you work from the right or you work from the left, you want to determine any of the bending moment, you are still going to get the same answer. Has someone calculated that of B for me? Bending moment about section B, please just type it there. 102. Thank you. That is 102 kilonewtons meters because it's force times distance. Let's calculate that of C. So for that of C, it is at this point here. We want to take moment about this section. So I'm going to walk from the right to that section. Now, you must remember that there is a force here, which is what? 16 what? Kilonewton. Now, so what I'm going to do here is that I have two forces, which is 60.5 and 16. So 60.5 is pointing up, isn't it? So that is positive. 60.5 multiplied by 2 plus 16 is pointing down. It's going to be minus 16 multiplied by what? Minus 16 multiplied by 2. It's multiplied by 2 because you can see from this point to this point is 1 meter. We are taking moment about, so that is going to be 1 meter is going to be minus times 3. Sorry, minus 16 times 3. Can someone give me the answer here? So it's going to be 1. This is going to be 1 plus what? Plus 2 to get to this point. 73 kilonewton meters. Thank you. So this is what? 73 kilonewtons meters. What is the bending moment about D? With bending moment about D as well, I'm going to work from the right hand side to the section of what? To this section of D. So I only have one force there, which is 16 what? Kilonewton, and the force is pointing down. So it's going to be what? Minus 16 multiplied by 1. So the bending moment about D is minus what? It's minus 16 kilonewton meters. So I'm done. So I've calculated my forces. I've calculated my bending moment about each section. So what I need to do now is the last question there that says that we must draw the shear force and the bending moment diagram. Okay, so this is what I'm going to do here, because let me write all the bending moment values here, because I'm going to need them. Kilonewton meter. So firstly, I'm going to write, this is 45.5 kilonewtons, and this one is what? 60.5 kilonewtons. Okay, let me draw the shear force diagram first. Let me draw the shear force diagram first. So I'm going to be using this line. Yeah. So there is a line here that I'm going to be using as a reference. Okay. Now, if you want to draw your shear force and bending moment diagram, it must be directly under the what? Under the beam. It must be directly under the beam. This is A. This is B. This is C. You can draw it graphically or you can just sketch it. This is D. And this is what? E. Now you must know that this side is the positive side. This side is the what? Negative side. I was supposed to draw my bending moment diagram just beneath it, but because there is no space, how is this done? So I'm going to put the dots, then I'm going to join them with a line. Okay, if you check section A, there is a force here which is 45.5. So according to your scale, if you want to draw according to scale, maybe a certain centimeter up, you indicate that here. 45 what? This is 45.5 kilonewtons. Now, this is B. Between A and B, we have a point load of 40 kilowatt newtons. Let me indicate that here as well. This is 16 kilonewtons. Now, between A and B, I have 40. Now, still using the sign convention, knowing the fact that if it is up, it's positive. If it is down, is what? Negative. Now, it's now going to be minus 40 plus 45.5, because 45.5 is facing up. So plus 45.5 minus 40. So at section B there is going to give us 5.5. So you measure, maybe this is just 5.5 kilonewton. So that's the second dot. This is the first dot. Okay, let's get all the point first. Now at that section B, we have 20 kilonewtons. newtons. We have 20 what? Kilonewtons. So it's going to also affect that force. So it's going to be 20, right? It's going to be minus 20 plus what? 5.5, because this is positive. So this is going to give us what? Minus what? 14.5. 20 minus 5.5 minus 5.5 is going to give us minus 14.5. So at that same section, you need to put another dot there. This dot right 14.5 kilonewtons. Okay, so that force is going to act until C. So at this point here on C here, we have 30 kilonewtons facing down. So it's going to be minus 30 minus 14.5. It's going to give us what? Minus 44.5. Minus 44.5. Between C and D, there is no force. It's going to be an horizontal line. At D, there is an upward force of 60.5, which is what? Positive. So it's going to be plus 60.5 minus plus 60.5, 60.5 minus 44, 60.5 minus 44.5. It's going to give you what? 16. So it's going to give you 16. So at D there, you can just put your 16 here. This is what? 16 kilonewton. Between D and E, we have another force that is pointing down, which is the concentrated force here, which is 16. So that force is pointing down is negative. So minus 16 plus 16 is going to give you what? 0. So it has to close. If it doesn't close, then you have a problem. So this is now how you are going to join your shear force diagram. Point from A here, there's going to be a straight line. My hand is not that straight, but just bear with me. There. Yeah, I'm going to draw another line again. Now, because there is a UDL there, uniformly distributed load there, it's going to, from there, it's going to be here. You can see. So it's going to be a slant line. So this one will be straight line. And then it's going to be straight line up until 14, up until 14.5 there, down there. That is a straight line. And then I'm going to draw another line. Between B and C, there is no force acting there. So it's just going to be a horizontal line. Horizontal line. Just going to tick in that. And then I'm going to draw another line. Okay. So there is another line to minus 44.5. There is going to be another line from between C and D, there is no force. It's going to be an horizontal line. You draw the horizontal line to D there. Can tick in it. And then you draw a straight line from that point up here to 16. And then you draw the last one there, which is the one that represents UDL to E. I'm just going to give you some minutes just to draw. So this is your shear force, what? Your shear force diagram. Any questions? 5.5 kilonewton. Yes, almost. Yes, it's going to be halfway. Yes, it's going to be halfway. Yeah, it's going to be halfway because the total length is what? Is 8. Yes, it's going to be halfway. You're right. So when you are drawing according to scale, this is how it must look like. So that's your shear force diagram. Let's draw our bending moment diagram. Okay, let's draw the bending moment diagram. So at this point here is where I need those values. So I'm going to be writing them here. Bending moment at A is equals to 0 kilonewton meters. Bending moment at B is going to be equals to, what did we get there? Bending moment B at B is 102. Bending moment at C, what did we get there? 73 kilonewtons meters. Bending moment at D, we got minus 16. Then bending moment at E is equals to 0. Okay, now the bending moment diagram is the easiest. So what we are going to do here is let's just draw. I told you that the shear force and the bending moment diagram must be beneath. The bending moment diagram must be beneath the shear force diagram. So because there is no space, that's the reason why I'm drawing this like this. Okay, so I'm just going to, I don't even need the beam. So what I'm going to do here, I'm just going to indicate the section. This is A, this is B, this is C, this is D, and this is what? E. So I'm just going to look for what's the bending moment at A is 0. That's my first point there, which is 0. Bending moment at B is 102. 102. That's the maximum bending moment. 1 or what? 102. Bending moment at C is what? 73. So it's maybe let me just put that here. 73. Bending moment at D is minus 16. You put your minus 16 here. Bending moment at E is what? Is 0. So the uniformly distributed load between A and B is going to be let me use another, it's going to be a curve, right? So the rest are going to be a straight line. This is how it's going to look like. It's going to be, oh sorry, straight line. It's going to be a straight line from here to here. I'm going to draw another straight line again from 73 to 16 here. And then because there is a UDL there, is going to be drawn in the other way. It's going to be a curve. So this is 0. So this is my bending moment diagram. Any questions?